Hi, Chris DeLeon here again. Now this is technically going to be the third video in the series for Introduction to Programming Real-Time Interactive Prototyping for LMC 6310, Computers and Expressive Medium. Even though it's the third video in the series though, there's a couple of ways the numbering is kind of funny. In one, the third video in our channel, you'll see if you keep up as a subscriber, that it's actually a video for the other class that's co-taught with it, LMC 6313, Principles of Interactive Design, and that involves PHP, web programming stuff. That's not a part of this series. Secondly, even though this is a third video, we're actually going to start by going back a few steps to talking about how to write code that's using just some basic structures, ifs, variables, loops, of both for and while variety, while using some text output rather than using graphical output through the void setup and void draw kind of construction like we've been doing. We're just going to be writing it straight into a new processing sketch. This may be a review for people that already have done programming of any kind before, in which case you may want to choose to skip this section. But for those who maybe haven't, I still think it's useful to see this after having a little bit of context from the earlier couple of videos about kind of how we wind up using it in this course, just so you don't get the wrong idea of kind of the programs that we write, which is why we didn't start with this. But I do want to stop and review just kind of what's a for loop, what's a while loop, what's an if conditional, how's it connect to an else, and so on. So for starters, remember that something I said we always put in every program is a void setup and a void draw. That we do this, whatever code we put into void setup will be called once when the program starts. Let's see, program started. This means it's going to print out program started down here in the console log. And void draw gets called every single update. Print line, program updated. And when I press play, it's going to open up a little postage stamp sized window. You see the program's updating constantly. When I close it, scroll all the way to the top, it says program started once, that's void setup being run, top to bottom of these braces, and then void draw being called top to bottom. And as I mentioned before in the other video, if I switch the order of these, if I move setup down below draw, it has no impact. It doesn't matter what order they're defined in, these are built in to be recognized by processing. That void setup will always be the entry point for code on the very first execution, top to bottom, program started. And then void draw will be called repeatedly as the program updates. However, void draw, because it happens every single frame, can make it kind of complicated if you're new to programming to figure out what these basic structures do, like ifs and elses and variables. So we're not going to have draw at all this time. Now we could just write code and setup. We could say program started, print ln, that ln is short for line, another line of code. We could we'll talk about how the for loop works here in a second. And I equals 0, I is less than 5, I plus plus. Print line, counting, line index number. Use a plus to concatenate the I. And when I press play, this will happen once because we have a setup but we have no draw function. So you'll see we have program started, another line of code, and then it has counting, line index number 0, 1, 2, 3, 4, each of the values for the for loop. Now the reason why it's opening up a postage stamp is because processing assumes you want to write a graphical application, but we're not in this case. We're just going to write text output. As long as all we're trying to write is basically the equivalent of a setup function, and processing it actually lets us leave out the setup. So now we're writing just lines of code that the program's going to run top to bottom. And this won't work with functions anymore, but it's, I think, a good way to introduce just some basic structures. So once again, if I press play, we'll see the exact same behavior as we would have if I would have just crammed all this into void setup, if we had it. It's kind of an alternative way to use processing. If you just want to make a single pass of code, draw something, perform some calculation, or in our case, just illustrate some basic functionality in a programming language. So this for loop can be kind of scary if you're new to it. So we're going to build up to that. The first thing we're going to talk about is a variable. So use a variable of type int, and we'll say int score. It's a good value to keep track of with an integer. Let's start that out at 0. Let's also say float speed equals 3.7. And now we can print out these values. Print line. Now for one thing, I can just put the values right in there. Score and speed. Actually, score and speed look a little too similar. I realize I want to make sure there's no chance that you accidentally look at one and see the other. So I'm going to use score in the word velocity. Now technically velocity also includes the direction, but bear with me. I just want a word that looks different. So down here you'll see the 0 and the 3.7. That 0 is printing out our score value. Velocity is printing out the 3.7. Now each time we do this kind of construction in code, it's referred to as declaring a variable. And there's 2 or 3 parts to it. Usually 3, technically you only need 2. The first is the type of the variable. So an integer, integers for, I'm not sure how much you remember these terms from math, but an integer is a number like 0, -5, 17, 1,000. It just can't have a fractional or decimal point. So 3.7 wouldn't count. -pi wouldn't count. But 0 is fine, -3 is fine, and so on. We can add discrete numbers to it. So again, we could add 7, we could add 14. If we try to add a fractional number, it's going to cut off part of the number, and we're not going to wind up with the number we're expecting. A float, by comparison, is a different type of number, and it keeps track of what's called a floating point decimal, which allows us to have decimal points. We can have a number that's roughly pi, of course approximated. We can have 0.1, we can have -8.6. So this is good for values that we need to be able to like decelerate smoothly, or if we need to draw a curve, we're going to probably get floats involved. And there's other types. There's more sophisticated and involved types like string, where we can have like a name in it. Larry. Just as an idea of some different types of data structures. And one of the things we do as we begin to program is we'll create our own data structures by creating classes and declaring instances of them. Now, it's not just a label, though. It's not just something which is a word we assign to a number. It's a container. And so we can actually change the value in that container at any time. Let's say I want to make the score now 2,000. I'll press play. And now, by the time the code gets to the part where it does print line on score, it's been set to 2,000. So the equal sign, as I explained in one of the earlier videos, but to go back through this, equal sign in programming does not work the way it does in algebra. It's not a statement of equality, it's a statement of assignment, where it takes the value on the right side of the equal sign and moves it over into the label on the other side. Now, because of that, it makes no sense in programming to say 2,000 equals score. I'm going to comment that out, which you might recall from earlier, that / tells the computer to ignore that line. But when it tries to get to that line, when we press play, it'll complain and stop us. Left-hand side of an assignment must be a variable, because we can't assign the value that was in score to the number 2,000. That's sort of a backwards thing. It's like, no, 2,000 is a container. Score is a container that'll accept that value. Now note too that all code doesn't happen at the same time. Sometimes because code happens so fast, it can confuse folks who are new to it and they start trying to think of it like it all fits together simultaneously. It is very much a line-by-line operation up until you get to parallel processors, multi-threaded applications, stuff that we're not going to deal with in a course like this. And probably you could go many years with programming and not have to think about. But so if I set this here to 34, when I press play, even though score was 2,000, at this point, it's 34. We then overwrite the value that was there. We tell it to make it now 34. And by the time it prints, it's been updated to 34. You'll see down there. By the way, so if you find these numbers down here, for example, too small to see, these videos are recorded at 1280 by 720. You can use the little gear icon in YouTube to increase the size setting to HD. It might take a second to load it, but then you should be able to full screen it and better see all the little text down there, because it's going to be important to see that, and I can't control the size of that the same way I can the text up in the programming box. Now let's say we don't just want to set it to a value, though we want to increment it by some amount. Well, how might we do that? Your first inclination might be, okay, let's say we want to add 34 to it. You might think score plus 34. The problem with that is that this is basically typing 2034 semicolon. We're not telling it what to do with that number. It would check the value of score. Okay, there's a 2000 in there because of the line above it. It'd add 34 to it, but it doesn't know what to do with it. If we wanted to assign it, we would have to say score equals score plus 34. And now when we press play, you'll see we have 2034 because it's filling in the value it had in the container, 2000, adding it to the 34, so now it's 2034, and assigning it because of the equal sign into score, which is updating our value. As mentioned in one of the earlier videos again, but I want to review as we build up these basic constructs. This is such a common operation in programming, I'm going to comment it out, that another way to indicate that same operation is to say plus equals, which is programmer shorthand for take the value that was there, add 34 to it, and then assign it back into the same container we got the value from. So this will have the same effect of adding 34 to it. These two lines are truly identical in their operation. Both will give us 2034. Now, as mentioned earlier, If I try to add 3.4, we're not going to get 2003.4. It's going to truncate it. We get 2003 because an integer can't save that 0.4 portion. By comparison, if instead we set velocity to 2000, oops, copy velocity. Hold on, I must be hitting the wrong button. There we go. Okay. Now velocity will be assigned 2000. When I add 3.4, you'll see 2003.4. We can keep track of that extra fractional point, and in fact, we have quite a bit of accuracy on that. We can add more decimal places. It's going to keep track of quite a few of them, as you can see there. And as for the name, we can also do operations on the name. We can overwrite the value of it. Sorry, my computer's being a bit laggy. Name. Now we can't assign a number to it. We can assign as a string, and quotes are how we delineate a string in programming. So we might say Bonnie, and then we can add on to it. Let me do some more parentheses. I'm going to put a space so it has a space after it, and Clyde. Might have misspelled Bonnie, but that's probably less important here. I'm going to press play. Down here we see Bonnie and Clyde, because it did this exact same operation. It overwrote the value in the label name, so it was originally Larry. If we stuck a print line name here, it would output Larry. We then overwrote it with a value of Bonnie. If we stuck a print line there, it would say Bonnie. And then we concatenated using the plus sign and Clyde onto the right side of Bonnie, so that when we finally print line name, we get Bonnie and Clyde. So there's some basic variable types. Let's do something more interesting with them. Let's go back to printing underscore value. Okay, so let's say we have a score, and we give the player 100 points for something. If score is greater than 50, print line, you win. Well, let's leave it at that for now. Okay, so in this case, we've added 100 points to the 0 score we started with. We have an if statement. It's just a reminder, so these white space things here are just for legibility. The program's equally happy if we did it like that. I'm just trying to draw attention to where those are. If this statement is true, if indeed score is greater than 50, and at this point of the code, of course it will be, it's going to be 100, then it's going to print out this statement. If I press play, it'll say I win. And if I don't, if I comment out this line that's adding the score to it, it will not say that we win, because it's not greater than 50. Now, we might check the inverse of that, because right now we're not getting any feedback. I could also say if score is less than or equal to. Of course, we don't use the complex characters that combine the less than or equal to like you see in math class. Here we can actually just use greater than or equal to, less than or equal to. There's also another one, not equal to is the exclamation point, and equals equals. Two equal signs is how we check exactly 50. But for starters, we'll get back to that in a second. If score is less than or equal to 50, you lose. So let's set the score to 50. And I press play. Now it says you lose. If I set the score to 51, then it's going to say you win. And again, maybe we want to handle the case where it's exactly 50. Greater than, less than, equals equals. You barely lost. That's how we'll phrase that. And just to be clear, the rest of the program is still here. You're just seeing me scroll in it a bit as I add more code. Still has the variable declared up here. We're adding a number to it. And then we're doing 3 if statements, which we're about to combine into an if-else chain. So it says you win because it's 51. When it's 49, press play. I lose. And if it's exactly 50, when I press play, I barely lost. Now, one of the downsides to this kind of construction is that partly, so let's say I just want to have 50 be my winning score, I would have to change that in multiple places at this point. Whereas really, if I don't win, I probably want to lose. I should be able to use something that says, okay, if it's not this one, make it that one. And so what we can use there is instead of saying if, again, I'm going to get rid of that one. I'm going to get rid of this in case just for a moment while I discuss this example. I can say else, and there's different ways you'll see people line these up. So in the same way as these if braces, some people like to put their braces on the next line, like so. My habit tends to be like this, and in fact with the else in particular, I tend to sort of combine it and link it tightly with the else, with the if before it. So now, if this condition was not true, so else, then it'll do this code instead. So now we're going to either win or we're going to lose. I run it, I lose. They're not greater than 50. I'll run it again with 51. Now I win. Now you might be wondering what's better about doing that, or how is that different than just saying if score is less than or equal to 50. Besides the fact the number is only in one place, if we change the number here, minus equals 5, so now let's say, okay, we were at 51, we go through here, it prints out our score, then our score is going to dip below 50, it's going to be 46, 51 minus 5. Remember, minus equals means to take the value that was in score, subtract 5 from it, and save it back into score, in this case. You might be wondering, is it going to say you win, you lose? And it's not, because once it's made its way into the if up here, there's no way you can change the values to make it go into the else. It's too late at that point. That's not the case if we kept these as two separate statements. So when our code looked like less than or equal to, if score is greater than 50, do this. Now, within that block of code for the if, so these braces indicate what applies to that if, we can subtract 5 from it, and now the program is going to say, you win, you lose. Because by the time the code gets to this point, this line, line 8, our line numbers are down here, the value has been changed by it in a way that else would prevent us from doing that. But like we said, okay, so maybe we want to have a special condition for, okay, if it's greater than, if it's less than, or if it's exactly. We can actually chain together ifs and elses. You barely lose. So if it's greater than 50, it'll say you win. If it's less than 50, or so otherwise, if it's less than 50, it'll say you lose. Otherwise still, so if it's exhausted this number of options above it, then it'll just use this as a fallback. So when I press play, I win 49, and I lose, and 50. You barely lose. We're back to the situation. So actually, so for one thing too, just to be clear, else if is one that you can use many, many times. So there are situations you might find code that look, it'll be different expressions inside the if, but you can chain together a whole line of if-elses to check multiple states, and each one below it in the chain will only be checked if all of them above it failed on the check, and as soon as any of them pass, nothing below it in that chain will be checked. Just as an idea about how ifs and else kind of relate to each other. Now, in this case, we still have this 50 in both places. Something we might say is we might say final int, let's see, score beat this score to win equals 50. Final tells the program that if we try to change this number, it should yell at us. And all capitals with underscores instead of camel casing lowercase is sort of the programmer's way of indicating to ourselves in the future, as well as to other programmers who look at our code, that this is in fact intended to be held constant and never changed. So when I press play, we'll get the same functionality we previously did, except I can change that number in one place. It's going to be updated all over the place. So now it's 80. That's no longer enough to win. You lose. And if I set the bar a little lower to 30, that's of course less than 50, so now we win. And again, that final word behind it, some programming languages use words like const, but in Java and for processing, it's going to be final. If I try to change that number later in the code, it's going to stop us. It's going to say you cannot assign it, it must be blank, and not using a compound assignment. It's a final local variable. So there's the idea of the final or the constant. There's some if-else chains. Now the if and the else are conditional. Another thing we do frequently in code is we do loops. So let's say we have score. I'm just going to sort of empty out our program a little bit. Let's say while score is less than 100, score plus equals random. Random is going to give us a number less than the number we tell it. So if I say 10, it might give us back a 0, might give us back a 9, might give us back a 7 or a 5 or a 4. It'll never give us back, though, a 10. It's inclusive on the left side, exclusive on the other. So it's going to be up to 9 again. And then we're going to print out the score of what our score is so far. Remember, this is not the amount that's being added to it each time. It's the current cumulative score. Print print line, we'll say player exceeded 100 points. And additionally, well, actually we'll get there in a second. Okay, when I press play, if we look down here at the console, we'll see it skipping along. So first it gave it 5 points, then added 2, brought us up to 7, added 9, brought us up to 16, and so on and so forth, up until it exceeded 100. Notice though, it still printed the score when it was over 100. Because the way that this while loop works is before it first evaluates, it checks and sees if this is true. So for example, if I made that number 1000, that's not less than 100, so in this case it would skip it. If it's false, it actually works kind of like an if statement. It'll never even go inside there. It just says player exceeded 100 points. It skipped this whole block of code because as soon as the program started, 1000 was already not less than 100. But again, the other point I wanted to call attention to was that it doesn't check. Oh, that one landed right on 100, so let me pick another example. There we go, 104 again. So it will not check the condition to see if it's true again until it completes all the way top to bottom. So even though at this point in the code it was already 104 after, so many laps through it, then it still printed out the score before it continued on outside of the while loop. Now something else we could still do, for example, we could count how many turns to win. We'll start the counter at 0. Each time that this loop happens, we're going to say plus plus. Now plus plus, if you don't remember from the other one, is identical to saying that value equals that value plus 1, which is identical to saying plus equals 1. It's just that so all three of these lines do the exact same thing, but adding 1 is so common that plus plus is kind of a shorthand for doing it. And we're going to add a new line, print line. It took plus turns. Since we're adding a random number, sometimes it's going to take more turns or fewer turns, and in this way we get to see how many turns it took. So here it took 22 turns. I'll press stop and play. This next time it took 25 turns. Next time I press play, 19 turns. And it's just counting up each time this while loop cycles. It's adding 1 to a counter, which we can then print out here. There's nothing built into while loop that's making that possible. It's just us adding that to it to say, okay, each time it does this, add that to it. Now there's a pattern going on here where we set the score value right before our while loop. We have a value which we check to see if this is true, then go ahead and go top to bottom in the code for that loop. And we have this thing which increments and keeps track of the change in it. Actually, in this case, score. That's such a, again, a common construction that exact same block of code could instead be written. Let me zoom this out a little bit. Actually, let me keep that on the screen up there. That body of code right there could also be written for int score equals 0. Score is less than 100. Score plus equals random. I think there actually might. There's a subtle difference here. We're not going to stress too much about that because it's a slightly more advanced discussion. Those of you who know programming more frequently know exactly what I'm talking about, and other folks, feel free to check it if you're curious, because I think you know there's a little trick here. Okay, but so all that matters is that the for loop is broken into 3 chunks, divided by semicolons. A section A, a section B, a section C. Section A happens right when the for loop gets there, so it's setting up the variable to be used. Actually, we're going to have to comment this out, because when you declare the int above, it would conflict with it to also declare it down here. So I'm going to comment that out. Remember the /* to // comments out multiple lines of code. So equals 0. And then the middle value, the B value, is basically what we would put inside the while to figure out, okay, as long as this is the case, continue operating internally, or give it another lap around that code on the inside of the for loop. And the third bit is how to increment the value, or what change to make at the end of each operation. So one way to think about this is that it's the start, the condition to keep going, and how to change it each time. And then included inside it is what to do for each lap of it. So here I'm printing out the score and counting up the turns. This should do very close to what we previously had. 24 turns, 1 second. Okay, I'm good. Okay. Now one difference is when in the loop it does this check. So you'll see here it stopped at 98 instead of 104. Now it stopped at 95. Oh, excuse me. Now it's stopped at 95. We'll actually get one more turn out of this while, having to do with when it does that check in the loop. But more often than not, we're not going to be that worried about it. Now, more often than not, instead of adding a random value each time, we're just adding 1. And we would do something, instead of wondering how many times it's going to take to calculate, we'll often want some sort of code that's like I equals 0, I is less than, let's say, 20, I plus plus, print line I, get rid of this other stuff. And this is basically telling the code to count to 20. It's going to start at 0, go up to 19. It's very, very common in a for loop to see a plus plus operator. Now the reason you're going to use these things is because, especially when we say have an array of objects or an array of other values we want to go through each of, we have basically a set of 20 different particles to move around, or a set of 20 different objects to make bounce. We're going to write a for loop which is going to give each one of the numbers in that set, the 0th, the 1st, the 2nd, the 3rd, its turn to run its code, to update its position and draw its new coordinates and so on. And a for loop is going to be our most common way of doing that. There's also a difference in that within a while loop, well, actually we're not going to get there too much. So okay, we've covered for, we've covered while, we've covered if and if else. Another kind of value, or another kind of construction we can use is called a switch case. So if I have int some value equals, let's say, 3, just for starters, I can do is switch some value, case 0, case 1, case 2, case 3, default. Each one of these will have a break. Now switch cases are seen by some programmers as very old-fashioned. They are much closer to the way machine code kind of works. They're much closer to the way assembly language works. They are not bound in the same way as most other control structures are in terms of braces. The switch statement itself gets a brace, but then each of the conditions within it instead has a break in it. And so let me show you what I mean by that. So print line, let's see here, value was 0, value was 1, value was 2, value was 3. There's other ways we write this kind of functionality, but I just want to point out the gist was less than 0 or, I'll just put a symbol here, greater than 3. There we go. Okay, when I press play, of course it's going to say value was 3. Default, the way default works is that if none of these cases above are satisfied, if none of these are a match for that value, it's going to check a sum value 0, a sum value 1, a sum value 2. This is kind of like an if-else chain, except it can't be as complicated. It can't be nearly as involved because we can't have conditional, we can't have, inequalities. We can't check if it's less than or greater than some value. All we can check is it one of these exact values, or is it none of them, and if so, apply a generic behavior at the end. And the default is optional. What happens if we don't have a break in there? So if I, let's say, some value equals 1, when I press play, it says value is 1. If I remove that break, which I could either do by deleting it entirely, or equivalently, just for sake of illustration, commenting it out. Oops, sorry. When I press play, it'll say value is 1. It's going to then fall right through into case 2 and say value is 2. Again, if we forgot our break there too. When I press play, value is 1, value is 2, value is 3. So if I set some value to 0, it'll get stopped there because of that break. Value is 0. And so a case where we're likely to see, for example, a switch case statement come up is when we're handling keyboard keys, because there's a long set of particular values that we want to handle. And so we might do like a case for different letters as they correspond to basically numerical values in the computer. And so we'll handle the A, W, S, and D keys in different ways in our response. And we might have a default case that catches, okay, if you push a key that's none of the buttons we wanted, maybe play an error sound to let them know that you're hitting the wrong buttons, or maybe display a help message to let them know what buttons we expect them to press. So that's a switch case. We've covered ifs, we've covered elses, we've covered some basic variable creation. And that's probably enough for now. I really just wanted to make sure we had some warm-up of these functions. Let's go back to that. Sorry about that. So in order to do functions, we're going to have to go back to having a void setup, because without void setup and void draw and things, it's going to get upset at us about knowing how it's supposed to flow through the code. Print line, let's say program started. Print line, program last line. And let's say our function. I'll call this do some stuff. Oops, okay. Void do some stuff. Let's talk a little about return values and about void functions. So when I make a function called do some stuff, I can put anything I want inside here. Actually, let's have do some stuff. Int I equals 0, I is less than 4, I plus plus. Print line I. So this is going to say program started. Remember, the code's going to jump straight to setup. It doesn't matter what order functions are defined in. It's going to jump straight to setup, say program started. When it gets to do some stuff, it's going to jump up to the function, do some stuff. There it's going to encounter a for loop, which in our case is starting at 0. So long as it's less than 4, it's going to keep adding 1 to it. And in the middle, in the guts of it, it's going to print out the current value. So it's going to 0, 1, 2, 3, each on their own line, because we have the ln here for print line. Then it's going to say program last line. Press play. Sure enough, program started, 0, 1, 2, 3, program last line. Now, what you've seen so far in the other examples is where we use a void here. And what that means is that there's no expected value to come back from it. It's just going to make some changes in the code. Or it's just going to perform some actions inside that function, sort of as a way of, we could kind of cut a body of code out of here and move it up to its own function. And the way that tends to happen, if you're refactoring, is we might have a mess of code down here. We find ourselves putting a comment, count to 4. To remind ourselves of what happens in this block of code, we're like, okay, that comment reminds me of what that block of code does. We can instead wrap it up into a function by saying void count to 4. Computer's being skippy. I'm going to cut that, paste it up here. And now I no longer need the comment because effectively the way that I named our function is the clue of what's supposed to happen at that line of code. Program started, count to 4 is now a label, a meaningful semantic label for this bit of code which is going to count to 4 for us. We can take parameters for it. A number. So what if we don't always want to count to 4? What if we want to count to different values based on something else in our program or based on some sort of user input? If I put an integer here, I can receive it in this value or in this inside this function by putting an int here and say count to this num. Now within the scope of this function, it takes on that label. Okay, so int count this num here is going to refer to 8 because I put an 8 there, and I could also put, say, a 3. And when I press play, first it's going to count 0 up to 7. Remember, because it's less than, it's never going to show the actual number itself. And then 0, 1, 2 because it's next going to count up to 3. Here we've been able to reuse this body of code with just one number difference of passing in a different value. That's what we're going to see throughout in various other uses of functions. And we could return a value. So let's say we want to add numbers together up to a certain value. So instead of count to a number, let's say add numbers less than. Okay, now we've got a more interesting situation. Int sum equals 0. Sum plus equals I. Now we're going to have a return value. See where we had this void before? I'm going to now make that an int. And what that allows me to do, let me first of all use our new function name, is we can treat it just like we would an integer, meaning we could print it out directly, like so. So this is going to compute, adding up all the numbers that are less than 8. It's going to start at 0, count up to the number each time, compound that number onto the sum that's accumulated so far, return that value. Returning means that we can treat the whole value like, or we can treat the whole function call like the value that got returned. Or we could even say int numbers less than 3 equals that. So So we could calculate it, and then we could say print line numbers less than 3. And as always, these labels for our function, for our variables, are purely semantic on our part, including the letter I, which is not very semantic, but it's a common one for a very short loop. We could call those elephants and daisies and things. The program would do the same thing. So print number, add numbers less than 8. 0 through 7 added together apparently equals 28. And add numbers less than 3. 0 plus 1 plus 2 gives us 3. That's why we have a 3 down here. And the return value, again, allows us to treat the whole function like the value that comes back out of it. Now, I want to point out something about scope, that this count to this num doesn't exist outside of these braces. We can't reference this value anywhere else in the program. It only exists within the scope of this function. Likewise, sum only exists within these braces. We return a value from it, but it can't be referenced as sum. It would have to be referenced as the function that we're calling that has a return value of type int. Now, what if this was a type void? Well, then we couldn't do a return value from it. We could use return to quit the function, to bail out midway, but this int is what tells us we can use it like an integer. We can make that a float, we can make it a string if we wanted to instead return an accumulated float value or a calculated float value or a combined string of some sort, maybe an access entry from a database or something. We can have multiple arguments here, int, multiply. And I think you're starting to see, yeah, so my brace is coming off this right side. I'm just going to shorten this variable name to count2. Hold on, my keyboard's acting funny. Oops. Alright, there we go. Count2, count2, there you go. Multiply, so let's say we want to return sum times multiplied by 5, multiplied by 10, then it's going to use this number inside here referred to as multiply. So for the first number it's going to be 5, second number it's going to be 10. I'm going to press play. 140 and 30 respectively, where it's doing the same calculation it did, then multiplying it by some other number. Okay, so this all seems very abstract, and it is, and it's part of why I don't like to start this way, so I like to begin by showing you the context from those first two labs about how we call functions. We can give them parameters, we can give them return values, we can write for loops. I think that helps situate something more abstract like this, and then meanwhile we kind of go back and forth a little bit to kind of walk through how basic functions and control structures like ifs and elses and for and while loops behave. So we go back to our program, then we have some more context to resituate in these high-level abstract ideas. These can be used for writing all kinds of calculations, performing all kinds of computation. It's not really what we're here in this class to do, though. Just want to help warm you up to some of these basic programming operations independent of a drawing application, since, again, as soon as we start doing graphics and in real time and on a plane with coordinates and things, there's some other things to keep track of mentally. But if you're confused about this program, really take some time to understand it. It's not terribly long. It's 15 lines of code. Experiment with it. Make some changes to it. Make it your own. See if you can figure out, after you make a change to how this function works, what number you'd expect to come out by calculating it by hand. See if you can try referring to variables by different labels in different places in the program. Figure out where they will and won't show up. Also, while you're programming, and you may even run into this problem already just trying to follow along, inevitably, if you're new to programming, you're going to sometimes miss a semicolon. You're going to sometimes miss a brace. And it's going to try to give you a hint. It's going to say, are you maybe missing a semicolon around this spot? As a warning, by the way, often that's going to tell you the wrong line because the semicolon is how the program knows where the semicolon goes. Likewise, if you're missing a brace, the program will be confused and lost. Unexpected token print line, because it's not expecting print line outside of a function, it needs to be inside a function. Now, I will suggest that don't take these errors personally. It's not like your assignment's being graded. You know, sometimes we're so conditioned from school that a red mark anywhere means we've done something wrong and that we should have known better. This is very much just a part of programming, getting compiler feedback, having it help you through catching some little stuff. There's some good habits you can stay in about indenting your code, so each time you do braces, you indent your code one more. Each time you close braces, you indent back. If you go to Edit, Auto Format, it'll also do its version of that for you. So if your code gets kind of out of order and you're having a hard time figuring out where your braces should be, Edit, Auto Format, again, will fix that for you. I don't recommend leaning on that too much. Other languages often won't provide that sort of nicety. But that's going to happen. You're going to miss some braces. You're going to miss some semicolons. You're going to miss some parentheses. Don't stress. Don't make a big deal about it. Best thing I can recommend is to make small changes to your program at a time. Try them out frequently. That's part of what's nice about processing. There's such a short compile time and run time to press play to get the output from the program to see if it's doing what you think it does. And then it's going to behoove you to develop a habit of hunting down, fixing, and trying to catch where those problems are, because they're going to happen to you all the time. I've been doing this now for half my lifetime. I still get all kinds of compiler errors and things, and you'll see me do it every now and then here. Maybe a little less so, if nothing else, because I have practiced teaching this kind of exact sort of pattern. But certainly when I'm writing my own games and working on my own projects, I'm all the time getting compiler errors. Again, don't treat it like it's like you're doing it wrong or like you're dumb or like you're not getting it. That's just part of programming. You just kind of get used to that feedback from the compiler. It's got nowhere else to be. You're not troubling it at all. Just take that feedback and work with it. But anyway, it's Chris DeLeon. Next video, we're going to be going back to graphical land. We're going to take what we had done in terms of splitting out that ball movement to bounce into a separate file. And we're going to develop it into a class with an array list to move the bouncing balls around, which was something I said we're going to do here. And it's really, of course, in lab we did this and then that. But I'm trying to keep this video shorter to split it up because we have kind of a long lab session. So hang in there if you're interested in that. I really think that after you've been through this exercise, even if maybe it's a little obtuse now, it's going to help you make some more sense out of the other ball movement code when we go back over there. We're going to be starting from scratch, though, as a kind of a bit of review, but come back soon and we'll have another video for you. Thanks.